relation between free energy change, that means del G, and composition of reaction system. Relation between free energy del G and composition of reaction system at constant temperature. Constant temperature. See, already we have derived one expression about the free energy. Del G is equal to VdP minus SdT. So, when a reaction is proceeding at constant temperature, dt is equal to 0, therefore SdT is equal to 0, therefore del G is equal to VdP. Next, if ideal gases are involved, we have PV is equal to nRT. Therefore, V is equal to nRT by P. Therefore, del G is equal to nRT by P into dP. Therefore, del G is equal to nRT dP by P. So, since temperature is constant, this term is constant, R is anyway constant. So, for if number of moles of the gas is constant, this entire term will become constant. Next, say at constant temperature, when reaction is proceeding, based on the change in the number of moles, the pressure inside the container continuously either increases or decreases, but in general it may or may not change. Therefore, if pressure changes, what is the corresponding change in the free energy of the reaction system? In order to calculate the change in free energy with respect to change in pressure, we have to integrate that above expression. Therefore, on integration of above expression, between P1 and P2, we get del G, G1, G2. Here nRT fixed. Now integrating this expression, P1, P2. Therefore, G2 minus G1, this is nRT ln P2 by P1. Therefore, G2 is equal to G1 plus nRT ln P2 by P1. If P1 is equal to 1 bar, then G1 is equal to G0. Therefore, G2 is equal to G0, because when pressure, if you take P1 as 1 bar, G1 will become G0. Therefore, G0 plus nRT ln P2 upon 1. If 1 mole of gas participate, G2 is equal to G0 plus RT ln P2. So, by using this expression, we can derive the another new expression to calculate the change in free energy in a reversible reaction. If the reaction of following type following type take place, if reaction of following type take place, that is m moles of the A is reacting with n moles of the B, it has produced x moles of the C and y moles of the D. If this reaction is at equilibrium, then if we apply this expression, then we can derive a new expression through which we can able to calculate the change in free energy at the equilibrium. Therefore, for A, that is the free energy is Ga is equal to G naught plus RT ln pressure of A. Similarly, Gb is equal to G naught plus RT ln Pb. Similarly, Gc is equal to G naught plus RT ln Pc. Gd is equal to G naught plus RT ln Pd. At equilibrium, the total change in free energy is equal to free energy of the products minus free energy of reactants. Free energy of the products minus reactants. Products means here C and D. Reactants means A and B. Therefore, free energy of the products C and Z. So, therefore, free energy of one product is this term. Free energy of the another product is this term. Therefore, total free energy of the C and D, Gc plus Gd minus similarly Ga plus Gd. This one. Therefore, Gc is this term G naught C plus RT ln Pc. Next, Gd plus Gd is this one G naught D plus RT ln Pd. This is the free energy of the products minus free energy of the reactants minus G naught A plus RT ln Pa plus G naught B plus RT ln Pb. Therefore, if we rearrange del G naught plus RT ln P, this is one product is C, Pc power x, Pd power y, then another one is P power A, Pb power n. Therefore, del G is equal to del G naught plus RT ln Q, where Q is called reaction quotient. Where Q is reaction quotient. Next, if reaction is at equilibrium, del G is equal to 0. Therefore, del G naught is equal to minus RT ln Q. At equilibrium, Q is equal to K. Therefore, del G naught is equal to minus RT ln Kp.